Today, I'm excited to share with you an insightful topic that plays a pivotal role in our understanding of the universe: how astronomers detect radiation from interstellar objects. The study of the cosmos has always fascinated humankind, and in recent times, we've made significant leaps in uncovering the mysteries of distant stars, galaxies, black holes, and more. But how do we know what's out there? How do we detect objects that are billions of light-years away? The answer lies in the detection of radiation emitted from these objects. Let's dive into the methods and tools astronomers use to uncover the secrets of the universe through radiation detection. Understanding radiation from interstellar objects. Before we explore how radiation is detected, it's essential to understand what we mean by radiation in this context. The word radiation refers to energy that travels through space, and interstellar objects emit a wide spectrum of radiation. This includes not only visible light but also radio waves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. Each type of radiation provides astronomers with different clues about the nature of the object emitting it. For instance, stars emit visible light that we can observe with the naked eye. However, many interstellar objects emit radiation beyond the visible spectrum, which we cannot directly see. Detecting these forms of radiation requires specialized instruments, and this is where modern astronomy shines. Telescopes, our window into the cosmos. The most fundamental tool for detecting radiation from interstellar objects is the telescope. Since ancient times, telescopes have been used to magnify the light coming from stars and other celestial objects. But today's telescopes have evolved into far more sophisticated instruments, capable of detecting all kinds of radiation. There are different types of telescopes for detecting different forms of radiation. For example, optical telescopes detect visible light. Radio telescopes detect radio waves. Infrared telescopes detect infrared radiation. X-ray and gamma-ray telescopes detect higher energy radiation like X-rays and gamma rays. Each type of telescope plays a unique role in helping astronomers detect and study objects in space. 1. Optical telescopes. Optical telescopes, which collect visible light, are the most commonly recognized type of telescope. However, visible light accounts for only a small fraction of the electromagnetic spectrum. While they are invaluable in studying planets, stars, and galaxies, they are limited because many objects in space don't emit much visible light. 2. Radio telescopes. Radio telescopes are crucial in detecting radio waves emitted by interstellar objects. These telescopes have large dish-like structures that capture radio waves, which are much longer than visible light waves. Objects like pulsars, quasars, and even cold gas clouds emit radio waves that optical telescopes can't detect. Radio telescopes allow astronomers to study objects that are invisible to the naked eye, such as the remnants of supernovae and the structure of distant galaxies. A famous example of radio astronomy's success is the discovery of cosmic microwave background radiation. This is the remnant radiation from the Big Bang and provides critical evidence about the early universe's formation. 3. Infrared telescopes. Infrared radiation is emitted by cooler objects in space, such as dust clouds where stars are forming. Infrared telescopes are designed to detect this radiation, which is often blocked by Earth's atmosphere. Therefore, many infrared telescopes are placed in space, such as the James Webb Space Telescope, JWST, which is helping astronomers look deeper into star formation regions and beyond. By detecting infrared radiation, astronomers can peer into regions of space that are obscured by dust in visible light, revealing hidden structures and processes. 4. X-ray and gamma-ray telescopes. High-energy events like black hole collisions, supernovae, and neutron stars emit X-rays and gamma rays. These forms of radiation are too energetic to be captured by optical or radio telescopes, so special detectors are needed. X-ray telescopes like the Chandra X-ray Observatory and gamma-ray telescopes like the Fermi Gamma-ray Space Telescope detect these extremely high-energy radiations. For instance, black holes, which don't emit visible light directly, can be studied by observing the X-rays emitted by matter as it spirals into them. These observations have helped astronomers understand black holes' properties and their impact on their surrounding environments. Challenges in detecting interstellar radiation. While we have these advanced tools, detecting radiation from interstellar objects is not without challenges. One of the biggest obstacles is Earth's atmosphere, which blocks or absorbs much of the radiation coming from space. For example, X-rays, gamma rays, and most ultraviolet light are absorbed by our atmosphere, which is great for protecting life on Earth, but limits ground-based observations. To overcome this, telescopes like the Hubble Space Telescope, JWST, and others are placed in space, where they can observe the full spectrum of radiation. Another challenge is the faintness of the signals. Radiation from distant objects is incredibly weak by the time it reaches Earth. Sensitive detectors and long exposure times are required to gather enough data to make meaningful observations. In some cases, scientists combine data from multiple telescopes worldwide to create more detailed images of distant objects, such as the Event Horizon Telescope's famous image of a black hole. Conclusion. In conclusion, the detection of radiation from interstellar objects is the cornerstone of modern astronomy. By observing different wavelengths of radiation, from radio waves to gamma rays, astronomers can piece together a comprehensive picture of the universe's structure, composition, and evolution. Telescopes are our primary tool for capturing this radiation, and each type of telescope offers a unique window into the cosmos. From studying star formation in infrared light to observing the violent interactions of black holes through X-rays, radiation detection reveals the rich complexity of the universe far beyond what we can see with our eyes. Thank you.